Hello everyone and welcome to today's Chemistry Daily Booster. This is number 16 in our Paper 2 series and it is on the advanced information for both foundation chemistry and higher tier chemistry. What we're going to do then is have a look at how we can actually extract metals. First thing, we need to know what an ore is. So when we talk about ore, that's just a rock or a mineral that contains enough metal to make it economical to extract. So basically our rocks will contain some metals, but if it's actually at a level that makes it worthwhile us extracting it, then we call it an ore. There are three you need to know. Malachite is the copper carbonate, bauxite, aluminium oxide, hematite, iron 3 oxide. So malachite is the copper, bauxite, aluminium, hematite is the iron. So in order to get these ores out of the ground, the first thing we need to do is carry out mining. Once we've actually mined the ore from the ground, we then need to process it in order to separate the metal from whatever it's joined to. And the way that we do that is going to depend on where the metal is in the reactivity series, which we can see over here. Now, obviously what we find is the position of carbon in the middle there is the critical bit. So where carbon is going to be the most important bit in determining the method we use to extract metals from their ores. We have two real options. Option 1, electrolysis. Downside here, it's expensive. Bonus, we can use it to extract any metal we like. Option 2, we can heat it with carbon or carbon monoxide. Advantage here is that it's cheaper. But the downside, it only works with metals that are less reactive than carbon. If it's more reactive than carbon, it will do absolutely nothing. So two options really, electrolysis or heating with carbon. If it's less reactive than carbon, we use the heating with carbon. If it's not, it's electrolysis. If we consider how we extract copper first of all, then what we're going to do is a two-stage process. First thing, we're going to roast that copper 2 sulfide in air, and that produces copper oxide and sulfur dioxide. Then we're going to heat the copper oxide with carbon, and we get copper and release carbon dioxide. So what we actually find here is that we have a redox reaction. Remember what we said, redox stands for reduction and oxidation happening at the same time. And what we can see is in this case, carbon is the reducing agent. We have a second option on how we can reduce our copper oxide, and that is by heating it with methane or with hydrogen. So our little setup of the equipment is down here. All we're going to do is have our copper oxide, which is the black powder in the tube. We then have our gas going in, which would be either hydrogen or methane, and we're going to heat it. Now you'll notice that we do have a little flame with the excess gas burning, and that's just because we can't just pump gas in without an outlet, because obviously pressure would increase explosions, not good with glass. But we also don't want something like methane just leaving and just filling the room we're doing this in, because when it builds up to a certain percentage in the air, we would have an explosive situation. Again, not great. The next metal we're going to have a look at is extracting iron. Now, in order to extract iron from its ore, we use this bit of equipment called a blast furnace. This is it on the right here. We have three raw materials, iron ore, or hematite, the coke, and limestone. So three raw materials that we're going to put into our blast furnace. So what we can see is at the top, the coke, the limestone, and the iron ore are placed in. We have waste gases that come out. And at the bottom you can see we pump hot air in at the base where it's yellow, and then we've got two bits that we run off, two liquids, the iron and the slag. What we'll do is we'll have a look at this process one stage at a time. Stage 1 then, our coke is going to burn in hot air to make carbon dioxide. Because coke is just solid carbon, if we're burning it in air, that means it's going to join with the oxygen to make our carbon dioxide. All balanced because carbon plus oxygen, which is O2, makes CO2. Stage 2. The coke is then going to reduce that carbon dioxide to make carbon monoxide. So what we're doing is we're going to be adding, obviously, the oxygen from the carbon dioxide to a separate carbon atom. Therefore, we're going to have 2 carbon monoxide molecules for each carbon and carbon dioxide. Step 3, carbon monoxide reduces our iron oxide into iron, and this happens at around 1500 degrees C. So we can see it's quite warm. What we have then is our carbon monoxide. That's going to react with our iron oxide. We will then make carbon dioxide and iron itself. Now, if they ask you to balance anything here, they would give you things like the iron oxide formula. So then all you need to do is obviously remember carbon dioxide, CO2, iron on its own, just Fe, you've got a periodic table to use, and carbon monoxide, remember mono is 1, so single oxygen. What we've done here then is we've made liquid iron, sure, but there are still some impurities in it. And these impurities would affect the properties of the iron that we create. So we need to remove them. The way we do that is by the limestone. So remember we added those 3 raw materials at the beginning. Limestone is the only one we haven't talked about. It is there to remove impurities. Limestone is just calcium carbonate, and when we heat it up, it undergoes the process of thermal decomposition. So our calcium carbonate breaks down into calcium oxide and carbon dioxide. What then happens is the calcium oxide that we've created is going to react with silica to form calcium silicate. So what we have, our calcium oxide reacts with the silica, and that makes calcium silicate. So what then happens is that is our slag, and that is less dense than iron. So we end up with the iron sitting at the bottom, and then we have the slag sitting on top, and that means we can just run the 2 off separately. The third metal we need to know how to extract is aluminium. Now, aluminium we normally find as aluminium oxide, and we've got to extract it using electrolysis because aluminium is more reactive than carbon. So we can't just heat it with carbon because it's more reactive, therefore nothing would happen. So we have to use electrolysis. Remember what we said about electrolysis? Split the word up: electro, electricity, lysis, splitting. So we're going to split this using electricity. What we're not going to do is just directly heat our aluminium oxide and create a molten aluminium oxide on its own. The reason for that is that it has a very high melting point, 2072 degrees Celsius. So in order to heat it up to that temperature and melt it would be really expensive. Instead, we dissolve the aluminium oxide in this stuff called cryolite, and that means we can then carry out electrolysis at just 950 degrees. So much lower temperature means it's going to be cheaper to get it to that and maintain that temperature. When we carry out electrolysis then, what we've got is our electrolysis cell, and we're going to line it with graphite. Now that graphite lining is the cathode, which hopefully we remember is the negative electrode. We then have these graphite blocks that act as the anodes, and the anodes are the positive electrodes. What we find happening then, when we flip the switch and the power runs through this, we're going to form oxygen at the anode, because remember oxygen would be formed from oxide ions, which are negative, so they'll be attracted to the positive electrode. And what we find is the oxygen there reacts with the graphite, which is a form of carbon, and we make carbon dioxide. At the cathode, which remember is the negative electrode, we will form the aluminium because aluminium has positive ions. So positive ions attracted to the negative electrode. This is just what we'll talk about. Here's our electrolysis tank. So what we can see, these are all our positive carbon anodes. This running around the edge is the negative cathode, and then we've got our electrolyte in the center there, the yellow bit. As we obviously turn this tank on, we're going to form carbon dioxide from the anodes, and then the molten aluminium will be attracted to the cathode, and we can just run it off from the bottom here. They can ask you about the half equations, so what happens at the cathode, what happens at the anode. So all we need to know is that our aluminium Al3+ ions are going to gain 3 electrons to make aluminium atoms. Whereas at the anode, we've got our oxide ions, O2-. They are going to then join 2 of them to make an oxygen molecule, O2. So we've got to have 2 oxide ions at the beginning. Because we've got 2 minus charges, or 2 negative charges on each oxide, we've got 2 of them, 4 negative charges in total. We also have to release 4 electrons there. The final ways that we can actually extract metals is through using living things. So we can look at the process of bioleaching first of all. This is where bacteria are going to oxidize iron and sulfide ions, so that we will see sulfuric acid forming when oxygen and water are present. That sulfuric acid will then break down copper sulfide ores and release copper-2 ions. So we can use bacteria as the key thing here. And there are some real key advantages to this. Low-grade ores can be used, these are ones that only have a small amount of metal present. It's going to be much cheaper than traditional mining and processing methods because we're using bacteria. They occur naturally, need no special treatment, no particular high temperatures or anything like this. And we're not releasing harmful gases like sulfur dioxide into the atmosphere. There are of course disadvantages. It's slow. We may also produce some toxic substances as byproducts of our bacteria's action. Second living option for extracting metals is in a process we call phytoextraction. So this is where we're going to be using plants that are actually really good at absorbing metal ions. What we do is we select one of these plants that is good at absorbing the metal ions, and we then grow it on the soil that contains this low-grade ore. We're going to add these things called complexing agents, which basically make it easier for the plants to absorb the metal ions from the soil. Let them grow. Once they're grown, we will harvest the plants, burn them, which produces an ash, and that ash has a high metal concentration in it. We then extract the metal from the ash as if it was a high-grade ore. So obviously depending on what we're extracting, heat it with carbon, electrolysis as a result. Key advantages then is cheaper again, there's less waste involved, smaller energy transfers, and it's close to carbon neutral because the carbon dioxide we release in the burning process is only what the plants have removed from the atmosphere as they're undergoing photosynthesis in their life. Downsides though, still slow, we're talking about plants growing, that doesn't happen overnight, and it may take multiple replantings before we've removed all of the metal from the soil. If there are any of the topics that we've gone through today that you'd like to look at in more detail, then you can look at our C6 playlist on the channel. Do have a little look in your revision guides and at some past papers as well to get a bit of a feel for the kind of questions that come up on this second chemistry paper. And of course, don't forget to join us again tomorrow for our next Chemistry Daily Booster.